Should be going. Okay, cool. So we're still in review though. So UART we said, so if you're looking at one of the lines, for example, like let's say this is the TX line. This sort of notation here, you see like D0, D1, where they're kind of like little boxes. That just means that you can kind of see it's both high and low at the same time. It's just to indicate that it could be either. It's not going to be high and low. It's just going to be one of them. So it's just showing that each of these little squares could be a 1 or a 0 that they're sending out, right? So we saw that UART usually sends 8 bits at a time. So you can see here, this is 8 bits. We have an optional parity bit, which we can use if we want some basic level security or an error checking. Then we have a start bit and a stop bit. This is usually for synchronization and for making sure that the slave knows when you start communicating. You can imagine that if the microcontroller is just sending a high for TX, right? The slave is not going to know when the data started. Is it going to maybe say that these were the 8 bits, or maybe these were the 8 bits? I'm not sure if the master was sending me just 8 ones in a row, or if they actually started the communication. It's a little unclear. So we have this start bit to make sure that the slave knows, okay, this is real data, and we can start with this bit, and then if we want, maybe we actually do want to send 8 ones in a row, and that's fine. But without this start bit, which is here, we're not going to know that that's real data and that we actually have communication. Great. So with UART out of the way, we can talk a little bit about I2C. Some people call it I2C. Those people would be wrong. I'm just kidding. Sometimes I call it I2C as well. Some people also call it TWI. I don't see this very often. But two-wire interface. You'll see that sometimes in like sort of old school data sheets. But the idea behind it is similar to what we just saw in a way, because we also use 2 wires. So master, slave. And what these 2 wires are called are SDA and SCL. So SDA stands for serial data. Serial data. This is what I'm assuming they meant when they made this acronym. And SCL, if someone knows if the A stands for something different, that'd be cool. SCL is serial clock. This is definitely not how you're supposed to write it. You can see here, this is already different. We don't have a TX and RX line. We have now a clock that's being shared between the master and the slave, right? So this is our first difference. Where UART was asynchronous, now we have a shared clock. We are now synchronous. So that's one of the first major differences in I2C. So it's a synchronous communication protocol. What's also interesting is that there's only one data line, right? Before we could send data on one line and receive it on a different line. Now we have to share the same line. So whenever I'm sending data as the master, I can't be reading data at the same time. I have to stop and then receive the data from the slave. So they call this half duplex. And you can imagine what that means is that this communication protocol is going to be a lot more complicated, because we can't just send a start bit, send the data, and stop. We now have to know who the data is coming from, if it's a receive or a transmit, which direction it's going in, and need to make sure that people aren't talking at the same time, right? So that's one of the drawbacks. It's a lot more complicated as a protocol. but you do get the benefit of just 2 wires, which is great. Now, what's interesting with I2C is that it's actually one of the most used protocols, especially for really small sensors. So little things like accelerometers, pressure sensors, little pieces people use in IoT networks a lot in like DIY projects. People love I2C, mostly because it's just 2 wires, but you can actually put more than one slave on this bus. So with just these same 2 wires, what I can do is have more slaves, more sensors, more chips, more microcontrollers I'm talking to. They can all just tie in to these 2 lines. Sorry for this very bad drawing. But essentially they would each have their own clock line and data line, and they would all be able to talk on that bus just with those 2 wires. We don't need to have a separate protocol for each one where the master now has to have an I2C communication separate with each one. And that's usually what you would have to do with something like UART, although there are theoretically ways around that. But the beauty of this protocol is that it's just 2 wires and you can attach so many different slaves to it. So it's super cheap in terms of pin count and amount of wires you need. So if my master were some microcontroller, it would only need 2 pins, and it could theoretically talk to about 128 different chips just with those 2 pins. And that's why people love it. It's a great protocol, just a little bit complicated. Any questions so far? Cool.
Yeah. I have a question.
Please.
What's the slave? I might have missed it last lesson.
Yeah, good question. So a lot of the time, especially with I2C and a few of the other protocols we're going to talk about later, in these languages you sort of need someone to direct the communication. So we usually refer to them as the person who's controlling the communication as the master. And oftentimes that's whatever microcontroller you're using. You are the master because you're initiating the communication and you're getting data. And a slave could be a little integrated circuit, a little chip you're talking to. It could be a sensor. It could be an ADC. It could be a DAC, digital to analog converter. It could be an external GPIO expander. There are so many different things that a slave could be. It could also be another microcontroller. You could be communicating with a microcontroller. And basically, it's just to indicate that it's not in control of the communication. The master usually will dictate how the communication works. Does that answer your question?
Yeah, thank you.
Cool. Any others? Okay. So remember TX and RX, we crisscrossed them before? SD and SCL do not. The data line connects to the data line, which is good, and the clock line connects to the clock line. So don't make the mistake of crisscrossing them by accident. Now, how I2C works is that it works on an open drain principle. So if you remember with open drain, the pin of the microcontroller can pull low to ground and send a 0 volts, but it can't pull high. When it pulls high, when it wants to send a 1, it'll just disconnect and let go of the bus. And that pin's going to float. So what would we do to prevent that floating? John? What would you say? How do we send a 1 on the line?
Sorry, I was eating. Voltage on it.
Yeah, so we're going to want to send zeros and ones. For example, our clock is going to toggle like this. And maybe our data is going to look a little different, but it's also going to want to be zeros and ones, right? So if our pins are operating on open drain, we know we can send a 0, but how would we send a 1? What about Raphael? What would you say? What would you say, sorry?
To keep it from floating, we use like a resistor.
Nice. How would we configure that?
A resistor to 5 volts.
Okay. Yeah, that's right. So it'd go to whatever logic level you're using. So it could be 5 volts. Let's say 5 volts. That's exactly right. And so by definition, in the spec for this protocol, you have to provide 2 external pull-up resistors to 5 volts. And often they're 4.7 kilo ohms. So basically what that means is that from the microcontroller, your communication protocol, to send a 0, it'll be able to pull down to 0 volts. And to send a high, it will let go of the bus and disconnect, and it'll float. And then this pull-up resistor will bring it up to 1. So well done. That's exactly right.
I have a question.
Yeah.
Why would you not just use a push-pull configuration here?
That is a fantastic question. It sounds like it'd be a lot easier, right? The main reason is because 2 things are sharing the same line and driving the same line. And since they're sharing a data line, they're going to both have to send data back and forth. And so we encountered that problem before where if one person is sending a 5 volts and one person is sending a 0 volts, you're going to cause a short in the system. So if they disagree on any communication, one sends 5, one sends 0, then 5 is automatically going to be connected to 0 volts through these chips. And then you're going to probably blow a fuse, maybe light the system on fire. And so that's why we do open drain. You'll see later on when we talk about arbitration exactly how that open drain helps us. But that's the main idea. It's because 2 things are sharing the same line and you need to make sure that they don't accidentally cause a short. Does that make sense?
Yes.
Okay. And usually it's not a problem from master to slave because the master is controlling most of the communication, right? It gets to decide what happens when. So you theoretically shouldn't have that scenario. But the biggest problem happens with multi-master configuration. So I2C actually supports having a second master or a third master show up and spoil the party with control over these lines as well. And so you have to be very careful.
And then these masters could also talk to each other?
Yeah, I think so.
Cool.
It's not super common, to be honest. I've never had to use it, but it is possible via the spec. So let's draw this a little better. Master, please. So usually it's drawn sort of as like, people call it a bus, which is kind of a weird word. I still don't fully understand why it's a bus and not a plane or a car or automobile, but it's supposed to be like a common bus for a communication protocol. If anyone has any better historical knowledge or understanding about that, that'd be cool to hear about. But these are the 2 lines. right? And then maybe you have more slaves here. Usually this is how it's drawn, right? I'll just draw an S. So each one would connect to the line. And this is why it's so nice when you have a lot of sensors that talk over I2C, because you can just keep popping them on. And it's really easy to deal with. Still only 2 pins from your microcontroller needed for all of these things. Now, we mentioned you have to put pull-up resistors. You do not have to put pull-ups for every slave. Right? That's not what we're doing here. If you were to do that, right, they all go to 5 or 3.3, then you can see you're essentially putting resistors in parallel here, right? And so you're decreasing the overall resistance. So all these 3 would be in parallel. All these 3. So you only need to put 2 for the whole bus, right? Just 2 pull-up resistors and that's it. Just something to remember. You don't need to put it for every slave, just for the whole bus itself. And it'll go up to whatever logic level your microcontroller talks at. So if it's 5 volts, then that's great. 5 volts is good. If it's 3.3 volts, that's fine. It can be 3.3 volts. 3v3 is the notation. And you have to make sure that your slaves also can communicate at that logic level. If it's a 5 volt slave and you're a 3.3 volt microcontroller, you're not going to have a good time. So you want to make sure that they always match. If you really have to use an integrated circuit or a sensor that is a different logic level than your microcontroller, then usually what you'll do is use something called the logic level converter. We've mentioned this briefly before. All it is a little chip logic level converter. And all it is a little chip that would convert, for example, a 3.3 volt communication into whatever you want, right? So you give it 3.3 volts on one side, you give it whatever voltage you want on the other side, maybe 5 volts, and then it'll turn those 2 lines into 5 volts for you. And you can connect whatever 5 volt slaves you want. Just to make sure you don't damage things and to make sure that communication happens properly. Cool. So many things on the same bus sharing the same lines. How do we make sure that what we say goes to the right person, right? Maybe I want to talk to this guy. I don't want this guy to know what I'm talking about. It's private, right? We can't just broadcast it for the whole community. So, and we don't want them to be confused, right? If I send something that goes to everyone, maybe they'll all reply with stuff and then the bus will have a lot of different garbage and noise on it at the same time. So basically what people did was they invented something called the address, right? You have these for your houses, you have it for your mail, post offices. So why don't we do that for our communication protocols as well? That's exactly what they did, and it makes a lot of sense. So basically, everyone has their own address, right? So maybe I'll say like address 1, 2, 3. And so what happens is whenever the master sends out data, they're going to have to send out the address. I say, hey, how's it going, buddy? I don't want everyone to reply. I'm going to say, hey, Faraz, how are you doing? And then whatever slave is named Faraz would know that I'm talking to them. And then they can reply back with whatever they want, right? That's all this is. We basically just gave a little ID to all of the slaves. And this ID needs to be unique for each slave. We can't have 2 slaves with the same ID, obviously, right? If you have 2 slaves with the same one, it's going to get a little messy, and you're basically going to end up with a bunch of garbage. So usually what happens is the ID for that sensor or integrated circuit is set in hardware. So great question, Courtney. Is it built into the slaves? it's hard coded essentially. You don't get to program a new address. Like I wouldn't be able to say from the master, hey, address number 1, please change your address to 8 or 9. And the way it's done is in hardware. So can you guys see this data sheet? It's a quick yes or no. I know Zoom.
Yep.
Yeah, third. Okay, great. Zoom doesn't really let you share full screens anymore, which is annoying. But Skype seems to be chill. So this is a chip, for example. This is something that we would see. This is actually something that we use in on the VCU. So this is a current sense amplifier. So basically, it measures current on our 12-volt bus. Also, actually, the voltage as well, which is cool. And it communicates over I2C. So let me just steal this, and let's put it into OneNote. Note. Cool. This is an INA 226. So it's a little current sensor that we use on the VCU to measure how much current is coming in from the 12-volt rail. And you can see here SDA and SCL, right? So these 2 pins would go to the VCU and you measure there. Make sure you have the common ground. Same as VCU. If you guys don't have a common ground, you won't be able to talk. And if you look here, A0 and A1, these are address pins. So in your circuit board layout, or if you're putting this on a breadboard, on your breadboard, you would connect these 2 pins to either ground, SCL, SDA, or your voltage supply. And that would lead to different addresses. So clearly I didn't plan this well enough because I need to take another screenshot. But if we go back to the website, table 2 shows the pin settings and corresponding addresses. So in hardware, you can change the address, but this is not changeable on the fly or configurable. This is sort of done once, and that's the address for the chip. So this is a lot of possible different addresses based on how you connect these pins, right? So if I connect A0 and A1 both to ground, this is the address I should expect to send to actually talk to this chip. And you can see that they've budgeted for a lot of different possibilities. That's basically in the off chance that you're using a different chip that has this address. Okay, well then I could, when I lay out the chip on my circuit board, I'll just route those pins to connect to these guys. Then I'll have this address. On the off chance I have already a separate device with this address and a separate device with this address, I can go to the next one. And I don't know if this is a little overkill, but they've done a billion here. I think it's 16 different possible addresses that you could set up hard-coded wise on your chip. So if I have nothing else, then I could just use ground and ground, which is what we do in the VCU, and we just have this one. Mahmoud?
Is there a reason they make it not changeable on the fly?
Probably so you can't accidentally ruin it. The idea is that it's supposed to be set to that chip, and all chips have a different address that you've set in hardware initially, and they don't want to make it possible for you to accidentally overwrite them and make them the same.
Yeah, that makes sense.
Yeah, but like theoretically, if you wanted, you could use 3 different sensors, if they have the capability, set them all to the same slave address, and then in your communication protocol, you could add an extra layer of info saying, hey, are you this new address I made up, ABCD? And then the slave would have to reply. But then the slave would also need to know how to reply to that. So it'd be a lot of work, and you'd have to reprogram the chip, and things wouldn't work so well.
I think that's how the BMS slaves work, actually. You set their address through software, and then you can talk to each individually.
Yeah, so that's a great point, because those are using UART, right? So they don't have this built-in slave address. And so you have to, like TI had to create that software to add another layer of addressing for you. And so because it did it for you, it's super nice and easy now. But without having done that initially, you have to do that extra work.
Yeah.
Can you send data to multiple slaves concurrently? Theoretically, but usually you send it to a specific address, because a lot of the times what you're doing is asking for data, because a lot of the times they're sensors. So what you're going to say is, hey, can I get data from you, I2C? And then they'll reply. So if you're asking for things from multiple slaves at the same time, it's not going to go well when they both reply at the same time as well. So usually we just do one at a time. In part, it's because it's synchronous, but it's mostly because of the half duplex nature. There's only one data line, and that has to be shared amongst everyone. So only one communication can happen at a time. More than one person can't send data at the same time. Otherwise, it's going to cause conflicts and create garbage on the bus. Okay, so let's look at an example here of what the data format actually looks like, right? So we said that, or we looked at UART already, and we saw that it had a start bit, some of your data, a parity bit, and then a stop bit. I2C has some similar things in terms of start conditions and stop, but in general, you can tell already it's a lot more complicated. So all this is one data burst, like if I put it in that way. All of this has to happen for you to send one thing. So same as before, you got to start somehow, right? You need to let the slave know that it should start listening, that you're going to send actual data now. Otherwise, if there's no start condition, those lines just idling high. We're not sure if the slave reads that as just all ones forever, right? So we have the start condition, and again we have this sort of notation where we see could be low or it could be high, could be any of these, and this is where you say the name or the address of the person you're talking to. So if we were talking to that INA 226 that's on the VCU, well, on the VCU, what we did was we connected these pins to ground. And we saw that that resulted in an address that looks something like this, right? So in this case, what the VCU microcontroller would send is the address, and it's 7 bits for UART for I2C. 1000000. Now that I've sent the address, I'm talking to everyone on my bus. So for example, let's say I have more than just one. I have a lot of people. Maybe let's redraw that. But if I have a lot of people, VCU, maybe this is the INA 226. In our car, we only have one thing on the I2C bus, so it's nice and chill. But it would send this address, right? So 1000000. Okay, I did one extra. And then everyone would listen, and they'd be like, "Hey, that's not me. Guess this one's not for me." But INA 226 would be super pumped because that's its address, right? So it receives its address. Now the master is going to tell it, do I want to read from you or do I want to write from you? Remember that we only have one data line, so we have to know if we're going to read or write. And it's exactly what happens in the next bit. The master says, I'm either going to read or I'm going to write. And a lot of the times, it doesn't really show here, but a lot of the times they show this pin to look something like this, read/write with a bar. And that bar just means active low, right? If I send as a master If I send a 1, then I'm saying I want to read. I want to read from you. I want to know your soul. But if I send a 0, I'm going to write. And that's what this little bar means, active low. The write is active when the master is sending a low, right? When the master sends a 0, it says, I'm going to write to you. When the master sends a 1, it says, I'm going to read from you. And it's going to expect data from the slave after this happens. Is the address bit size a standard I2C thing? Or is it different master? Standard I2C thing. 7 address bits is what the I2C spec is. And you can imagine this gives you 2 to the 8 different possible addresses, right? 2 to the 8, 2 to the 7. Sorry, 2 to the 7. What am I doing? 2 to the 7 different possible addresses. So that's a lot. That's like 128 or something. So 128 different little sensors could be on your bus line, each with their own address, and you'd be able to talk to them all. Usually people don't go that high because that's a little aggressive, and communication is going to slow down because you can only talk to one thing at a time. But 7 bits is standard for I2C. If you go higher than this, if you go higher than the 128, which I've never seen, there is an expansion in the I2C spec where they say, okay, you're a little greedy, but I'll let you do a 10-bit address. I've never seen this. I'm sure there are applications where people use this. But again, I haven't used it before, especially to that nature of 10-bit. I've only just used 7-bit addresses, and that's been more than enough. That's a lot. So 7 bits is a standard, but in this, and you can, I've mentioned the spec a few times. Not all communication protocols have a specification. I2C is really buttoned up. NXP and Philips made the specification for it. So because it's so complicated, you really need to make everything clear. What I like about other protocols like SPI is that sometimes it's annoying because there's no spec if you're testing it or whatever, but it's so easy to use. You can do whatever you want. Like you start a data transmission, and like I could just put whatever I want in here. I could put 8 bits, 16 bits, 32 bits. I could say hi, hello. I could put an address if I wanted. Don't have to. It's chill. But with I2C, it's a lot more involved because you only have one data line. You have to share that. So what did we say? We said, I'm master. I'm going to say what address I want to talk to. So I said, okay, I want to talk to the INA226. I want to talk to my current sensor. What's up, bro? I have your address. I'm going to call you. INA226, I want to write to you. So I would say 1000000, right? So this is the address part from up here. The next thing I would say is I'd put a 1 for my master. Sorry, I want to write to you, right? Is that what I said? I want to write to you. So I would put a 0. Right? We said the write to write is active when the master sends a 0. It's active low. So I'd send a 0. I want to write to you. Then we take a little break, right? The slave digests this. It's like, okay, I'm ready. I'm ready to accept information. Then we start again. We say, now that I've established the address, now that I've established that I'm going to write to you, and I skipped the most important part. Sorry about that. This little guy here. I've established the address. I've established that I'm going to write to you. But now you have to confirm. You need to confirm with me that you're even there, that you're acknowledging what I'm doing, what I'm saying. And we call this an ACK. It's short for acknowledge. Right? I've given you an address. I've given you a read or write command. I've done all this work up front. I need you to work with me here. So I expect the slave or whoever I'm talking to then send this ACK back to me. And it's a little confusing because this line is shared, right? Both the master and the slave and all the other slaves communicate over this one line. It's a little bit tricky to understand who's talking when. But this is all master. So start condition, address, read write, and then the master lets go of the bus and it expects the slave to then drive the bus low, right? Remember, we operate an open drain on I2C, right? So if we expected a high, like a high ACK, like for ACK to be equal to 1, we don't know if that means that the slave just let go of the bus on purpose, or if the slave is not communicating, or if there's no one home, no one's there. So we don't really know what a 1 means on the ACK side, so we expect it to be a 0, right? We expect it to be low. If it comes back as low, the master is reading this. If he or she sees a low there, then it knows that the slave has acknowledged, and it can continue. Sometimes people call this a knack, just because it's active low. But the main idea is that it's an acknowledge, right? So what have we done? We've said, as the master, we're going to send the address to know exactly who we're talking to, not them, not them, not them, our friend, the current sensor. Now we're going to tell it, okay, in this case, we want to write, so we're going to send a 0. And now we wait. The current sensor needs to put in a little effort too. It needs to drive the bus low and send a 0 so that we know it's alive. All right, we get the 0, we're pumped, we can actually talk to this thing. Now let's say I want to configure some register, for example. Whatever I need to do, I can do it here. This is where I actually get to send my data now, right? Now we're done with the address, with the read-write, with our first ACK. We can send whatever data. If we want to write to a register, we can send the register we want to write to. We get an ACK. Then maybe the next thing we do is we send the data we want to put in the register. Then we need another ACK, and so on and so forth, right? And the master can keep writing as long as it wants. It gets to control everything, right? And that's what we do in the car, right? In the VCU. David Cow wrote a really great driver for us to talk to this INA226, our current sensor. And so what he does is he has to actually configure the current sensor first, right? So first thing he does is he says, hey, current sensor, I'm going to write to your register, right? I'm going to write to your register. And in there, I'm going to program the full scale range I want, the current sensor shunt resistor I'm using, all those things. So you'll say the register, and then the INA226 will ACK, they'll acknowledge, and then you'll send exactly what data you want to put in the register, excuse me. Then the INA226 will ACK again, and so on and so forth. And this whole cycle is stopped when the master then sends the stop condition. And very clearly from my drawing, that's here. All the stop condition is with SDA low, you let SCL float high. Let it go high, and then SDA goes high after that, and that's a stop condition. Then the slave knows it can take a rest, right? Now, what if the slave doesn't act, right? If we don't get an acknowledge at any point, then we just assume that all the transmission has been garbage and we didn't really get anything across. So we'll start again. And then it's up to you on the application level what you want to do if you keep missing the acknowledge, if you don't get that confirmation that your signal is going through. Now, if you want to read, very similar, right? If I want to read, we'll just draw the two guys for now, just so it's a little clearer. So these peeps wanna chat. All right, current sensor here, NA226, and VCU is here. These are my two lines, and they have pull-ups, right? Let's just leave that for now. So let's send the address. Let's send the address. I want to read, sorry. And we said that we totally erased it, but we said that that bit, we call it the R/W bar. So the write is active low, right? So when we want to write to it, that write will be active when we send a low. When you want to read, The read will be active when we send a high. So we're going to send a 1. Okay, send a 1. Make sure we get the ACK. Take a little break. And then after this point, we should be able to, instead of us sending data here, now this is the slave sending data back to us. So that's what you do for something like an ADC, for example. Now let's say you want to read a specific register in the ADC. Maybe there's 4, 5, 8. There's more than one. What you would do, you can imagine, you write first, right? Send the address. I'm going to write, and I'm going to say, usually the ADC will have a special command where you write to it and say, I want to read something from you. So it's going to write to the ADC and say, I'm ready to read register 4, maybe, right? I'm ready to read that register. Then the next thing you do after the slave acknowledges, the next thing you do is you restart this whole thing again. You send another command, and now you want to read. And then you expect the ADC to send data here for you. Questions? That was a big chunk of information dump. Does that make sense? Basically, the master has the authority to start and stop communications, to decide if it's a read or a write, to decide who to talk to in whatever situation it wants, right, via the address at the start. And what's nice is that we get a little acknowledge every time. So we get a little confirmation that, hey, I'm still here, I'm reading. John, do you have a question?
More than one. Yeah.
Cool.
What would happen if more than one slave responded?
Yeah, that's a great question.
What if like some weird things happened?
So the thing is, we're not going to be able to differentiate, right? If two slaves are trying to talk at the same time, so let's try and draw that out. What would that look like? Let's put it here. Have another slave, and it's gone rogue, or someone set the address to be identical between these two, which is very, very bad. And it's like, hey, I don't care. I'm going to talk to you at the same time. I like talking. It's not a big deal. So what would happen is that if my slave 1, so let's say it sends a high, like the very first bit it sends is a high, right? And let's say I'm also sending a high, so that's good. Next bit, my current sensor sends is a low. That's great because I'm also sending a low, so that's the same thing. Just that is going to appear on the bus. But now let's say my current sensor is sending a high, and then another high, and another high, and 3 highs, right? Remember, because it's open drain, for it to send a high, it's basically let go of the bus. So it's relying on the pull-up resistor to do that high for it, right? Now my rogue sensor, I'm not sending a high, I have different data to send. I'm sending lows in all these cases. So I've now asserted the bus, I've connected it to ground. I have an open drain capability, but that means I can drive the bus low, or I can let go to be high. This sucker here let go of the bus. The current sensor said, hey, I think I'm going to send a high. That's fine, I'll let go of the bus, no problem, it'll be a 1. But my rogue sensor is driving the bus low. So it's going to dominate. So what the VC will actually see back is this. It wouldn't see this because the bus wouldn't be pulled up high. It would be driven low by your rogue sensor. So you have to be careful because you sent data, you're expecting to talk to the current sensor, but somehow you have a rogue sensor with the same address, and it's sending back its own agenda, right? So while you think you're getting data back from the current sensor, Maybe getting data back from like a voltage sensor or some other thing that has the same address by accident. And so who knows what's going to happen? Everything's going to be completely messed up. But that's sort of a thought experiment of how it would work. How does it deal with the not acknowledge? Basically, it just sees that as an error and then tries to restart the communication. If you keep seeing repeated errors where the slave is not acknowledging, then you'd probably just abort and call a fault on the system. For us, could we completely remove all I2C and use SPI and CAN instead? Or will there be situations where we must use it like an IC? Yeah, that's exactly right. You're very dependent on what your IC is going to use. If the IC you pick talks over I2C, you're not going to be able to talk to it over anything else. You have to obey by what it wants to talk to. The only way you could change that is if you have a microcontroller, you have a VCU. You also have you have your current sensor, right? It talks over I2C. But you don't like I2C or I2C, so you want to convert it to CAN somehow. Sorry, to SPI maybe. I'm not sure if there are converters. Is that a thing? I2C to SPI converter? Maybe. Like, maybe you could, there's a chip you can use that will just convert them. That could be an option. Use some sort of converter here if you really hate I2C. But now you're just adding cost and complexity to it, especially if you already had an I2C bus ready to go from your VCU. And if there is no chip that automatically does this for you, you have to put another microcontroller in between. That would take in the I2C and send out the I2C and then convert it to SPI with exactly the right messages you want. So no matter what, you're going to have to put something in between if you want to change it. Or change the chip, right? Find a different chip that uses SPI. And that's usually the easiest solution when you're in the design phase. More questions? Those are good questions. So you can imagine the nice thing about I2C is you can put so many different things on that bus, but you're not going to be able to talk super fast, right? It's going to be slow because you're sharing this one serial data line, SDA, for both your master sending out data and every slave sending back data. That's the nature of half duplex, is a little slower. So often the communication speeds are at 100 kilobits per second and 400. Those are the two of the most popular standards. There are, so this is like normal mode and fast mode, I think. That's what they call them in the spec. It does get faster if you use things like they call like ultra high speed mode or whatever. You can get up to the mega. But usually it's just this, and not all sensors will support this, right? Whatever you're using is going to basically define the window of speed you can go. And so this will just tell you at what speed your clock line has to be, right? SDA will then have to toggle at 100 kilohertz or 400 kilohertz or 1 megahertz to send things back and forth. So often you'll see if you have just a pure ADC, like all it's doing is just sampling voltages and converting them from analog to digital. You just have a pure ADC and you want it to be super fast. You have a really fast sampling rate, right? It's super great. It can sample anything. Sampling rate, really fast. You'll see most ADCs come out with SPI. Just because it's much faster than I2C. Like if you look on DigiKey, it's most of them are SPI. You'll see some I2C, but by nature they won't be as fast. So if you're looking for speed, SPI is the way to go. And personally, I like it because it's much easier to work with. The spec is non-existent basically, so you can do anything you want. You don't have to abide by addresses. You don't have to abide by sharing the same data line, ACKs and NACKs, even though they're useful. You can just send whatever you want across. So it's a lot easier to use. But to be fair, I2C, all of that is built into your hardware, right? All you have to do on the VCU side is basically set if you're going to read or write. So you're going to set read or write. Set address you're going to send. And then set whatever data you're going to send, right? If you're going to read from a register or write data to a register, those are the only 3 things you have to do. So it's pretty good. And we use it for that current sensor because that's what the built-in protocol is for that. Any questions? So a couple of chat questions. Thoughts on I2C? I think it's good. I think it's a useful protocol, especially if you're limited on pin count. So you'll see like when you are, like, let's say you have a wireless or maybe like a wearable you've designed, right? And it needs to operate like as a little tiny device. And you're probably using an 8-bit microcontroller, something really small with low power. And maybe there's only like 16 pins on that chip, right? Maybe it's tiny, like this is the microcontroller. In contrast, VCU has 144 pins, so that's a lot. If you're limited on pin count, you have a bunch going to GPIOs, you have some going to ADC, you have some going to PWM, you have some going to power and ground. You probably want to limit the number of pins you're using for communication, so with just 2, you're able to communicate to all your sensors. So I think that's a really good application of I2C. In my mind, if you have the pin counts available to you in the space, and you don't have to route your wires physically across long distances because SPI has double the wires, then I like SPI, especially because it's faster and easier to use. Raphael, how much slower does I2C get for each new slave that's added? Well, you can imagine, right? If I'm talking to slave 1, it gets all my attention. I can chat with it whenever I want. I don't have to share with anyone else. I add a second slave. Now I have to talk to it, and then I have to talk to the other slave. I have a third slave. I have to talk to the 3. So for that same amount of time I had, I now need to split it 3 ways. So you're basically just chopping up however much time you have to talk over I2C between your slaves, right? So to do the same amount of work, it's going to be a lot slower when you add slaves because you have to communicate with all of them and then wait for them to talk back. So there's like a weird scenario in I2C where you have multi-master mode. It's not very common, like I alluded to earlier, but it does happen. And the question now is same as before, sort of what John was asking. What happens when they want to, and now you don't have a rogue sensor. This is a totally legit case, right? Master 1 wants to talk and Master 2 want to talk. They should theoretically both have equal say to the bus because they're both masters. So who wins, right? Who gets to actually talk first? And it's very similar to what we mentioned before. It's a process called arbitration. And basically the idea behind it is whoever sends a 1 first loses. So let's say they both want to talk to the same slave, right? So they know they're going to set a start condition, then they're both going to set the address. So 1000000, right? Which we know is the address of our INA 226. So if this were the INA 226, INA 226. So I want to talk to him too, so I'm going to send the exact same thing, the address, right? And then I want to read, so I send a 1 after. That's all well and good. Then the INA 226 acts on the line, so pulls this low. And this is reading the same thing, right? Because it's connected to this same line. Now I want to send some, so if we said read, it's not as fun. So we want to write. Right? So we want to write. So we sent a 0 to write to it. But we want to write different data, right? I want to send 1 1 0 0 and then 0 1 1 0. And my other master wants to send 1 1 1 0 0 0 0. Right? It kind of looks like a 6. So they both send a 1, right? They start off with a 1. This is trying to send a 1 as well. That's all well and good. They'll send a 1. It's the same thing, right? If they're sending the same data, they're both letting go of the bus. And so the bus is being pulled up to 1. That's fine. The other one sends a 1 as the next one. That's fine as well. I send a 1 twice. Sent a 1 twice. And this is sort of a weird situation so far because you have masters colliding, but they're colliding exactly perfectly where they're sending the exact same data. And now here, similar to how the slave worked, now I want to send a 1, so I'm going to let go of the bus. Master 1 will let go of the bus and hope to send a 1. But Master 2 has no idea what Master 1's planning and says, well, I want to send a 0 instead, right? So it's going to put a 0 and pull that line down to ground. Since it's open drain, it has the capability to pull down to ground, but they don't have the capability to drive up, right? So they have to let go of the bus for it to be a 1. So Master 1 let go, but Master 2 drove it to ground, right? And so Master 1 is reading the bus as well, right? It's reading what it's sending, right? So it sent a 1 and it checks the bus. Yeah, I have a 1. Sent a 0. Yeah, I have a 0, 0. Yeah, 0, 0. This is great. I have the bus basically. Sends a 1, 1. It's trying to send a 1 now, but it sees a 0 come on the bus because Master 2 drove it low and they share that same line. So Master 1 says, hey, I was trying to send a 1. Now I see a 0 on the bus. That means that some other master is trying to drive it as well. So I'm just going to let go from here. I see that you're trying to do the same thing I am, and I notice that you've driven it down to 0. That's fair. You have control right now, so I'll completely let go and stop sending. And Master 2 will now keep going as usual, as if nothing happened. But Master 1 will give up. And that's why I2C is open train. There's only one data line. There's only one SDA. And it has to be shared amongst everyone. Amongst the slave, amongst Master 2, Master 1, any other masters and slaves that want to talk on that line. And so how they arbitrate who wins, who gets to talk, is by using open drain, making use of it. Because with open drain to send a 1, you have to let go of the bus. You have to let it float. Whoever is driving the bus basically will control it. So Master 1 will say, okay, it's time for me to send a 1, I'll send a 1. Checks the bus, but sees a 0 instead. That means that someone else drove it down to 0. Essentially, if it let go of the bus and it doesn't see the bus float and get pulled up back to logic high, it's going to know that someone else is driving it low. So it's going to be a little sad and it's going to have to wait its turn, but it'll stop sending data. Master 2 will go, do whatever it needs to do, get out of there, and then Master 1 will take over. And theoretically, this could go on indefinitely. So like sometimes I like to joke that if we have a multi-master mode and I'm Master 2, I'm going to try and send as many zeros as I can to always have control over the bus first. and like I'll pad all my data with more zeros, and then just use the last 4 bits for data, just to control. But I don't think that's the thing people do, and this is not super common. But try to do to understand why I2C is open drain, like Mahmoud asked at the start. Why is it not just push pull? And it's mainly for this arbitration reason, so that we have a way to decide who wins, because we only have one line we have to share. Questions? Does that make sense? Yash, could you explain it back to me? How arbitration works? Cool. Okay, Yash will type it out. How about Elena?
Yeek. That was a lot of information when you brought in the second master, so I'm
Yeah.
gonna have to rewatch that. I low-key zoned out because that was
Okay.
too much for me. Sorry.
No worries. No worries. What about Raphael?
I think it's when you send a 1, it lets go of the line so that the person sending zeros kind of controls it, and then I guess it controls the whole line.
Yeah, essentially, to send a 1, we have to let go, right? And then we rely on the pull-up resistor, like you said before, to pull it up high for us. But whatever we send, we're also checking to make sure what we sent actually showed up, right? So you can imagine masters as a little bit insecure, right? They're putting something out there in the world. They're not sure if it's going to be accepted or not, so they have to kind of double check. Like, I sent a 1. Is it a 1? Is it a 1? Is it a 1? Okay, it's a 1. Great. I'll send another 1. Is it a 1? Yeah. Okay. Cool. But I'll send a 1, and by sending a 1, you're letting go, right, of the bus, and you're letting it float. So you send a 1. Is it a 1? Oh no, it's actually a 0. I didn't mean for that to happen. That means that someone else came in and sent a 0 while I was trying to send a 1. And that means that by a prior agreement, according to the I2C specification, if I see that happen, I will let my master friend have the line. And I'll let go and not do anything else. I'll let them control, since I've noticed that what I tried to send didn't actually show up. Is that clear? Does that make sense? Yeah, you copped out there. I saw you stop typing. Cool. Jared, do you have any questions? Yeah.
Is there not a more intelligent way to do it? Skill master?
Multi-master?
Yeah.
Do you have any suggestions?
No, I only have questions.
I don't know. Clearly not. Apparently, this is what they decided.
Chip select.
Ooh, yeah, baby.
Love for master.
I like chip select. Yeah, I don't know how two. Can you have 2 masters in SPI? I don't know. Sabrina?
You run the risk of potentially shorting your pin because of this.
No. Good question. Why no?
Because it catches on fast enough. I don't know.
No, because we're not push pulling, right? We don't. None of the masters are driving the pin to 1.
Right.
They're letting go. So they basically essentially disconnect. They go open drain. And then the way we get a 1 is via the pull-up resistor, which saves us from that shorting condition. So if master 2 is forcing a 0, sorry, if if master 2 is forcing a 0,
Yeah.
then the pull-up resistor won't cause a short because there's a resistor in between power and ground there. Does that make sense?
Yeah.
Okay, thanks for asking. Johnny boy, what you got? Lay it on me.
So obviously the most beneficial thing for this is that you can have one master with like 128 or like more, whatever, with different sensors that you can communicate to using one channel. Is there any other large advantages of using this communication protocol?
I'd say that's the biggest one, and also just the fact that it's only 2 pins. It's not particularly quick, and there's a lot of overhead, as you've seen, with how much stuff you need. But people really like it with small microcontrollers with limited pin count, and the fact that you can talk to a lot of things, just sending different addresses, and it's all built in. You don't have to write the software layer over top that includes an address in your data send, right? Like in UART, all you're sending is 8 bits, right? There's no address. So you could theoretically say, okay, 4 of my bits will be the address, and then the next 4 will be the data, and then you have to do all the software to actually handle that on both sides. So that's the main advantage. Exactly what you said. Small pin count, talk to a lot of things at the same time. That's it.
Cool. Also for we're using I on our car for primarily because like do we have a lot of sensors or?
That's a good question. So it's actually, let's see if we can show you. Where would that be? Here?
Ooh.
Oh no. Okay. So this is the VCU, right? This is the TMS 570 here, right? This chip. This is the INA 226. So it's a little, tiny little current sensor. And what it does, 12 volts comes in through here, and there's a shunt resistor we call. So this resistor is meant to handle all the current coming in. That's why it's so fat. So it can do about 1 watt, I think, of power. And it's 1 milliohm. You can imagine if all your power flowed through something that was like a kilo ohm, you'd burn a lot of energy through I squared R, right? So really tiny resistance to try not burn energy. But what this current sensor does is it measures the voltage drop across this tiny little resistor. And so it says, okay, I measure the voltage, I know V, I know the resistance, the VCU programmed into me through the registers that I'm using a resistance of 1 milliohm. So I know V, I know R, I can find I. And that's all the current sensor does, right? It finds the current flowing through there. And it's fine for us because it's just on the same circuit board, I squared C 2 lines. And that's just what the sensor outputs. It doesn't output SPI. And it's nice because I squared C is low pin count, and we're using SPI in 2 different applications already on this chip. So theoretically it has 5 available, but we use I squared C in this one. And it's just defined by the chip, right? This is the chip we wanted to use, and it does I squared C. Luckily, our TMS 570 can do I squared C as well, so great, that works. And if you zoom in here, these are actually the pull-up resistors that go up to 3.3. And like if this weren't blurry, you'd read that it says I squared C pull-ups, but they're just 4.7 kilo ohm resistors that go up to 3.3. A good tip whenever you're laying out a board like this is that these communication protocols, especially when you do it for the first time, go wrong a lot. Like you can imagine you write the code for it to talk, you hit run, and then you just don't get anything back. You're like, all right, what are the 100 different possible errors that could have occurred? So what we do is we use something called the logic analyzer. So I've stolen this notebook, but it's called a logic analyzer. Really useful for communication protocols, because what it can do is basically record all the data passing on your lines and generate a little plot for you that looks like exactly what we saw before with the ones and the zeros on the data. As long as it has the probes to actually electrically connect to those lines, right? And so often what people do on circuit boards is they route test headers. So if you look here, there's these three little header pins with access to SCL, SDA, and a ground, just for good measure. So I can plug in my logic analyzer right into these pins, and I know that these wires are coming from here and going all the way to my chip, but I can intercept them in the middle and just connect my analyzer. And on my computer, I can now see exactly what's being sent back and forth. So it's incredibly useful, especially the first time you're talking to a sensor, to see what's actually happening. If your data is going through, if the sensor's talking back, if there's no acknowledge, if the address is wrong, if your read-write bit is wrong, if it's the wrong voltage level, if there's just no data, maybe there's a hardware disconnection somewhere. And so it's like so useful to be able to monitor these signals when you're testing. And so I always recommend whenever you have a circuit board you're designing with some sort of chip or sensor that communicates over something like this, always have these test pins you can connect an analyzer. Here's the SPI to our digital to analog converter, our DAC. Again, all these pins are part of SPI, and we can monitor them with the analyzer on the bench while we're testing. Same with UART. So here, UART, RX, TX, ground. I2C we said already. CAN is up here. So it's really important to design your board to be able to be tested so you can figure out what went wrong with it. And to be honest, everything went wrong with every single communication we did when we started writing code for this board. It's just really hard, especially the first time you're doing it. Everything will go wrong. And you never know if you did the layout wrong too, right? You may have routed a pin backwards or connected the wrong address pins to ground, maybe connected them to a different pin, so you have a different address. So it's really important to be able to test what you're doing. And everything went wrong for us when we did it. This SPI didn't work. This I2C did not work. UART did not work to the PC. CAN did not work. And it was very difficult. But due to the great work of our embedded team, now I2C works, SPI works, UART works, CAN is working mostly. And we're super happy. There's another SPI that goes out. But embedded team's done a great job, and a lot of that has been because we can actually see what's happening there with these test points. So there you go. That's all I have for today. We've asked a few questions at the end, so if anyone has anything else.
You mentioned it a couple times. Why 4.7K for pull-ups?
Yeah, that's a good question. This is one of those things where it's sort of being the de facto standard recently, not recently, but just in the history of I2C. Basically, it defines how fast your edge rate is, right? So if I have a transition from high to low, if you zoom in, it's not going to be perfectly flat, right? It's going to be some slope to it. If I have a really high resistance, like let's say I put 1 mega ohm, this transition would be very slow. Right? It looks something probably like this. If I put 1 milliohm, I realize that looks similar, but 1 milliohm, you'd basically be shorting 5 volts to your line. 1 milliohm is like no resistance, so this line would always be at 5 volts and it would never go to ground. Right, so you don't want to go that low that you're shorting it with basically no resistance. But let's say I wanted like a 10K, right? That's reasonable and that works, right? You could put a 10K. It's just going to be a tad slower, but I've used 10Ks and they work just fine. So 4.7 is the rule of thumb, but anything around there works. Some people use 2.2Ks. Some people use 1K, but that's getting a little low in my opinion. That would give you a really fast edge rate if you use the 1 kilo ohm. But edge rate also relates to EMI. So the faster you're transitioning a signal, the more electromagnetic interference you're generating around that. So what often happens is when you have to do your compliance tests, sometimes you have to decrease the edge rate because it's too fast and generating a lot of noise. And so people put slower pull-ups, or if they have a push-pull system, they'll drive it a lot slower to generate less noise. And that keeps the system a little quieter and cleaner. But so far, people have found 4.7 to be a good balance of fast enough, but not so fast that your edge rate is generating noise around it. Does that answer your question?
Yep.
Cool. Okay, thanks, guys. Mahmoud, feel free to take it away.
Thanks, Gabe. So I guess this is a controls meeting,
I guess so.
but it's the same, pretty much the same people from